The next we are having the adsorption isotherm. Adsorption isotherm, see, we all know that the rate of adsorption depends upon the temperature. Rate of adsorption depends upon the pressure. As the pressure increases, the rate of adsorption also increases. So adsorption isotherm, it's nothing but it's a one which gives the relationship between the rate of adsorption, that is the extent of adsorption, and the pressure is called at a constant temperature, and hence it is called as adsorption isotherm. Iso means same, therm means temperature. So here we are making the temperature constant. So this gives the relationship between the rate of adsorption and the pressure at a constant temperature, and hence we called it as the adsorption isotherm. Here we have the Freundlich adsorption isotherm. Freundlich adsorption isotherm. So here it gives a, this we have a Freundlich equation which gives the relationship between the rate of adsorption and the pressure. So let's see what is Freundlich adsorption isotherm. The Freundlich adsorption isotherm equation is x upon m is equal to kp raised to 1 upon n, where x is a mass of adsorbent, m is a mass of adsorbent, k and n are constant, and p is a pressure. X is a mass of adsorbent, m is a mass of adsorbent. Means I can say that this x upon m tells us the rate of adsorption, the rate of adsorption per unit mass of adsorbent. So ultimately I can say that this tells us the extent of adsorption. That means how much adsorption has taken place, which is directly, K is a constant, so I can say directly proportional to the pressure raised to 1 upon n, that is the pressure raised to some fractional power. So here but we all know that this relation changes as the pressure changes. At low pressure the relation is something different, at high pressure the relation is something different, at intermediate pressure the relation is something different. Now let's see how it changes, as how this thing changes when the pressure when we are changing a pressure. So at a low pressure, first one, at low pressure, what happens at low pressure? At low pressure I can say that here the 1 upon n is equal to 1, and if 1 upon n is equal to 1, that means I can say x upon m is equal to k into p, and if the k is a constant, then I can say that x upon m is directly proportional to pressure. Means the rate of adsorption increases linearly with the increase in pressure. The second one, if at a high pressure, what happens at high pressure? At high pressure, I can say that 1 upon n is equal to 0, and if 1 upon n is equal to 0, that is x upon m is equal to kp raised to 0. Kp, anything raised to 0 is 1, that means x upon m is equal to k, and if x upon m is equal to k, it means the rate of adsorption becomes constant. It means the rate of adsorption does not depend upon the pressure. Then at intermediate pressure, what happens when we have intermediate pressure? At intermediate pressure, 1 upon n value is greater than 0 but smaller than 1, and if 1 upon n is greater than 0 and smaller than 1, then I can say that x upon m is directly proportional to pressure raised to 1 upon n, that is x rate of extent or rate of adsorption is directly proportional to the pressure with some fractional power. So in this case the rate of adsorption is exponentially depends upon the pressure. So as the pressure changes, the relation changes, and we can see that difference in the relation in a graph also. Okay, so we will see that relation, how the things are changing with the pressure. Before that, suppose if I wanted to know the value of this constant here, then how to know the values of this constant? So for getting a value of this constant, I will say simply that taking a log on both sides. So let's take a log. So we'll have log of x upon m is equal to log of k plus 1 upon n times of log of p. So we have this equation, and somewhere this equation looks like y is equal to mx plus c, or I can write c plus mx, because here we have to calculate these two things. So we are going to plot a graph of this and this. So this is y-axis and this is x-axis. This will be on y-axis, this will be on x-axis, this will be the value of m, and this is going to be the value of c. C, that is a y-intercept, and 1 upon n, that is a slope, because it is a value of m. So let's plot the graph for this. So when a graph is plotted, it is a graph of log of x upon m versus log of P, that is pressure. So here, since the graph appears like a straight, the y is equal to mx plus c, so it is a straight line equation having a positive slope, that is from bottom to top, with some intercept, that is a y-intercept also we have. So the graph will be something like this. So whatever the slope you will get, that slope will give you the value of 1 upon n, or I can say n will be nothing but the 1 upon slope. And this value will give you the log of k value. This is nothing but the log of k. So from the y-intercept you will get the log of k, and from the slope you will get 1 upon n. Whatever the value you are getting, take anti-log so that you can calculate the value of k also. So for getting the value of n and for getting the value of k, we can use this method. Okay, now for this, if I am plotting a graph of, it's a log of x upon m versus log of pressure. If I am plotting a graph of extent of adsorption versus pressure only, that means there is no log and something. So if the graph is plotted, this is log of, x upon m, that is the rate of adsorption versus pressure. So as the pressure increases, rate of adsorption goes on increasing. So first it increases linearly, then it becomes constant. The graph is something like this. First, at a low pressure, it increases linearly. So from this till that point, I can say that this point that it increases linearly. And if it is increasing linearly, that means I can say x upon m here is equal to nothing but, or it is directly proportional to P. That means in this case, I can say that here the 1 upon n is equal to 1. From here to here, I can say that there is a exponential change, that is a curve shape. And if it is a curve shape, then in this case, I can say that x upon m is directly proportional to p raised to 1 upon n. That means here the 1 upon n value is less than 1 but greater than 0. So exponential change in a curve, and then beyond this, that is at a high pressure, I can say that here 1 upon n is equal to 0, and if 1 upon n is equal to 0, that is x upon m is directly proportional to, or it is equal to k. And it is equal to k, that means the rate of adsorption or the extent of adsorption does not depends upon the pressure and becomes constant. Now at this point, I can say that x upon m becomes constant. So this point is called as saturation pressure. This pressure is called saturation pressure. Saturation pressure, that is a process, this is the pressure at which the rate of adsorption process reaches to the equilibrium state. So at saturation process, the adsorption reaches to equilibrium. Equilibrium means I can say where the rate of adsorption and the rate of desorption becomes equal. That is the rate at which the gaseous molecules are getting adsorbed on the surface, and the rate is equal to the rate with which the gaseous molecules are moving out of the surface. So since the rate, both the rate becomes equal, so the rate of adsorption becomes constant. The next we have, after adsorption isotherm, the next is the adsorption isobar. Adsorption isobar. Isobar means here, iso means same again, and the isobar means it is at a constant pressure. So this tells us the relationship between the extent of adsorption and temperature. at a constant pressure, and since the pressure is a constant, that's why the term isobar is used. In this case, the temperature was constant, and the relation was we were studying the relationship between the rate of adsorption and the pressure. Well, in this case, I can say that here we are learning the relationship between the extent of adsorption and the temperature, and in this case, the pressure is constant. We all know the relationship between the temperature and the rate of adsorption. The relationship is, if it is a physical adsorption, then the rate of adsorption decreases with the increase in a temperature, because the process is exothermic and hence it is a favorable at low temperature. So being an exothermic process, the rate of adsorption goes on decreasing as the temperature goes on increasing. This is for physical adsorption. Now what happens in case of chemical adsorption? The chemical adsorption which requires activation energy to start the process. Again, it's a rate versus temperature in Kelvin. In case of chemical adsorption, first the rate of adsorption increases with the increase in temperature to a certain temperature, and then beyond this the rate of adsorption goes on decreasing. So till certain temperature, the rate of adsorption increases with the increase in temperature. That means till this point, because till that temperature it gains the energy and its activation energy goes on increasing. Once the reactant molecules or the gaseous molecules get activation energy, after that the increase in the temperature decreases the rate of adsorption. So this is for chemical adsorption. So this is about the adsorption isobar, means where we are learning the relationship between the extent of adsorption and the temperature at a constant pressure.